Imagine we had a function as that shown in the blue, from the blue line here, and we wanted to find the distance shown in the red here between a point A and B. Now this would actually be pretty easy, right? Because we just need to use Pythagorean's theorem and we could find that like a right triangle, right? It's pretty easy. Now imagine we wanted to find the distance of two segments that look like that between A and B. This also is pretty easy, right? We just use Pythagorean's theorem twice for each of those segments. Now imagine if we wanted to find now imagine if we had a function such as shown here, f of x equals x cubed over 6 plus 1 over 2x, and we wanted to find that arc length between these 2 points shown in the red here. And we'll call that distance L. So you want to find L. Well, now this is hard, right? Because we can't use Pythagorean's theorem to get that. It's curved. And this is why we need calculus, because when we're dealing with curved lines like this, things get harder. So in this video, what we're going to do is build up to how we can use calculus to determine this length here, and we'll build up to what that actual length is for this particular equation. We're not going to solve the integral that we get analytically, though. That'll be left to a new video. But the point of this video is just to build up and to kind of give you an intuition of how we arrive at our equation. So we can initially take an initial approximation here and just say, let's take this straight line from this first point to the next. And this isn't too hard of a calculation. We just need, we could just say that length in the red there, we could say it's approximately, obviously it's going to be an underestimate. In the black dashed line there's going to be an underestimate, but it's going to get us in the ballpark at least, right? And we'll say it's approximately, using Pythagorean's theorem, the square root of delta x squared plus delta y squared, where delta x is going to be that distance in the x direction here, as shown here, and delta y is going to be that vertical distance shown here. And in order to find these, we can define this point as point 1 down here and point 2 up here, or point 1 is at x1, y1, and point 2 is at x2, y2. Now our delta x value we can simply find by taking x2 minus x1. In this case, it's 4 minus 1 or 3. Our delta y value also you can find it as y sub 2 minus y sub 1 from point 2 and point 1. And this is a little more involved because now we got to take the function value at 4 and the function value at x equals 1. And then so we go ahead and plug in our f of x for x equals 4, and we subtract our function where x equals 1, and in this case we'll kind of go through how to solve this in more detail here than we will later, but just to be rigorous here, we'll go through this. So first thing we're going to just want to do is simplify this a little bit, so that 4 cubed just becomes 64 and the 1 cubed just becomes 1. We're just multiplying some things out here. Now we're going to want to get common denominators in each of these, so the common denominator here is going to be 24. So this is going to be equal to 256 24ths plus 3 24ths minus 16 24ths. So now we can just add and subtract those numerators, and we're left with 243 over 24, which is 10.125 for our delta y. Now that we got delta y, we can plug that in to that equation on the top, and so we have the square root of 3 squared, where 3 was our delta x, plus delta y squared, where our delta y was 10.125, and this becomes 10.56 as our approximation. And it's not the best approximation, but at least it's getting us in the ballpark. So we'll call this our n equals 1 estimate, where n is the number of line segments we have. And so you might be able to see where we're going with this. Here we have we're using one secant line. And now imagine we want to get a little bit better estimate. We can use 3 segments, or 3 secant lines here. So in this case, you can see here on the graph we've got 3 of those dashed lines, and as you can imagine, this is going to be a better approximation. It's still going to be a little bit of an underestimate because you can see like the red segments are a little bit longer because they have some curve to them than those straight dashed black segments, but it's going to take us on the right track. Our total length of this is going to be the length of each of those segments, and this is L1 here, L2, and L3. And by L1, L2, and L3, those are going to be the red. Those are going to refer to the red arc segments there, not to the black dashed lines. And so we can say L1 is going to be approximately the square root of delta x1 plus delta y1. It won't be exactly, because again we're defining L1 as that red arc, not the actual value that we're finding here. So because we're just doing an approximation. So in this case, our delta x1 we find similar to how we found delta x earlier, and we're going to use p. We're going to call these points p sub 1 and p sub 2 that we're looking in between. So our delta x1 is going to be that x value between p sub 2 and p sub 1. And our delta y sub 1 value is going to be that y value between p sub 2 and p sub 1. And similarly, we can approximate L sub 2 using, now we're going to throw in 0.3 here, and our delta x2 is going to, you can see graphically it's going to equal that, and our delta y sub 2 is going to equal that height difference between 0.3 and 0.2. Lastly here, we're going to calculate L sub 3, and we're going to find that that's going to be the square root of delta x sub 3 squared plus delta y sub 3 squared. Okay, so now we kind of know that generally what we're looking for here for L1, L2, and L3, but now we got to explicitly define what delta x1 is, delta y1, etc. We got to get actual values for these. So similar to how we did before, we can find them. And one thing to note here is that you can see that delta x1 is going to equal delta x2 is going to equal delta x3. You can see that graphically over here. You can see that they're each equal to 1 actually, but the reason they're all going to be equal to each other is because we divided this into segments intentionally with equal widths in the x direction. So delta x is just going to be x4 minus x1, where that's the total x difference in our 2 points p1 and p4 here, divided by n, where n is the number of segments. In this case, n is 3. So our delta x is just going to be 4 minus 1 over 3, which is just going to be 1. As you can see from the graph, our delta x value is going to be 1. Now delta y is a little bit more involved, because you got to find the actual function value for each of these, just like we did before. So our delta y1 is going to be y sub 2 minus y sub 1, which means we're going to have to plug in our function value for x equals 2 minus our function value for x equals 1. And if we do that in a similar way as we did before, we end up with 0.917 for delta y1. And now we found that, we can go ahead and plug that in to our L sub 1 up here, and we can get approximately 1.357 when we take the square root of those two delta values squared, added to each other. Next we can look at delta y sub 2, which is going to be, using the same process, going to be 3.083. We plug that into our L sub 2 equation, 3.241. Lastly, we're going to go ahead and add that in, and then we're going to find delta y sub 3 at 6.125. Throw that into L sub 3, we get 6.206, which is just a little bit bigger than our delta y value, and plug that into our L approximation. And adding all three of these lengths together, we get that our length is approximately 10.804. So this is our n equals 3 estimate, and as you can imagine, we got a little bit more faith in it, because it's a little bit, the black lines that we essentially calculated that the length of those black dashed lines, and that's a bit closer to those red arc segments that we're looking for. So we're making some progress here, we're getting better. But we can do even better than this. And one way we can do even better than this is rather than use 3 segments, how about we use 100 secant lines? So that's going to get us pretty close, right? It will, but of course it would take a long time to do that by hand. So what we can do is get this into a summation formula. So we can say our length is approximately the summation from I equals 1 to n of the square root of our delta x squared plus delta y sub I squared. And you see in this case our delta x, we don't have the sub I in our delta x right here, because we don't actually need it, because our delta x's are all the same. So it doesn't matter what I increment we're on. The delta y is going to change, because as you saw before, our delta y values change depending on what increment what segment that we were looking at. So let's first just test this out for our secant line that was our n equals 1 estimate. Now I can actually do the summation in DESMOS. I won't go through all the details of how we get this summation, but essentially using the same process that we showed earlier. But you can see here that I have my sum from I equals 1 to n, and I'm just going to say n equals 1 in this case, which is basically means I'm just doing the same thing I did for the n equals 1 estimate, this line across here. And you can see when I plug in my summation formula, I'm getting 10.56, which is the same thing as we got earlier. So it looks like we're pretty well on the right track, and we just confirmed that our summation formula actually works. So we're getting the same estimate for our n equals 1, 10.56. Now let's say we ratchet this n up to 3, and now we can moment of truth here and see if our DESMOS formula actually works for n equals 3. And you can see here that we're getting 10.804 when we have our n value equals 3. So this is exactly what we had earlier, 10.804 for n equals 3 estimate. So this is good. Now we sort of confirmed our summation in DESMOS is on the right track, and now we can just go ahead and ratchet that up. So this is the beauty of this of the summation formula. Now we can just ratchet up that n. So let's say we ratchet that n up to 100. So instead of 3 right here, let's just make that 100. And you can see that we're getting approximately 10.875 right here as our summation value. So we can imagine that that's going to be a bit more accurate of a value here, 10.875. So this, based on our summation in DESMOS, is going to be our n equals 100 estimate, which is we have a bit more faith in at this point. And that's our estimate. So now we can actually move on to finding the exact arc length. And for this, we're going to need to use some calculus. So if we want to find the exact, we can take the limit as n approaches infinity. When n equals 100, that was pretty high, but we can, if we ratchet it up to the limit as n approaches infinity, we will get that exact length of our arc segment here. And of course, you're familiar with the definition of the integral, where if we take the limit of the summation as n approaches infinity, we do get the integral. The only problem here is that you can see our limit of this summation here as n approaches infinity is not really in the form that we wanted in down here. You can see down here you have this function of x sub I, and then you have a delta x it's multiplied by. We don't really have it in that form here. So the first thing we got to do is get this into a form that is like this limit down here, so we can convert it into an integral. So let's just say we're looking at this segment here in the middle, and we're going to use our delta x value and our delta y sub 2 value for essentially the rise and the run here. So of course the slope is going to be rise over run, and the slope is f prime. We can also call the slope f prime of x. In this case, f prime of x sub I is going to be equal to this delta y sub I over delta x. So you can see if we're looking at a particular segment, the slope of this segment is just the rise over the run. So it's delta y over delta x. So we can solve for our delta y here and say delta y is f prime of x sub I times delta x sub I. So we can then go ahead and take this delta y we found, we can plug it in up here, and you can see now we've got everything in terms of x. And this is actually going to help us get our summation into a form as is shown down here, where we can actually apply the definition of the integral. So our limit, now we can just sub out that. So now we can just sub out that delta y sub I for our f prime of x sub I times delta x. Now the question arises here, what do we mean by f prime of x sub I? Because if you look at this segment here, you can see there's not really a constant. There's a constant slope for this line that we're doing, sure, but when we're looking at f prime of a given x value, we're taking the slope at any given point. So you can say in between x equals 2 and x equals 3 here, there's several different slopes that we could potentially choose from in here. So that creates sort of some ambiguity on what we mean by f prime of x sub I. But let's look at what happens here. So say that we're trying to find our f prime of x sub I, but our x, we're ratcheting our n value up to infinity. That means our segments are going to be infinitesimally small. And you can see is if I zoom in here on any given point, if I zoom in far enough, pretty soon this just looks like a straight line, and the slope is going to be constant no matter where I choose it. So basically what we're showing here is that when you ratchet n up to infinity, it doesn't really matter where you choose to take that slope, because these line segments are going to be so small that if I took the slope here or if I took the slope here, it's not going to matter. They're going to be the same slope when I make these line segments small enough. And that's why it doesn't really matter if we use that, close this out, if we use that, if we call x sub I this x down here where x equals 2 or x equals 3, it matters if you have if you're doing big segments like this. When you get an infinite number of segments, it's not going to matter. So that's why we can keep this in here. Now we just got to do a little bit of algebra to our summation here, and we can see these delta x values we can just pull out. So we can just we can sort of factor out that delta x squared to the front here. And once we factor that delta x squared to the front, now we can just pull that out of our square root here. So now we have this limit of delta x times this function of x sub I. So now we're getting something that's much closer to our definition of the integral down here. And in fact, at this point, we can just use the definition of the integral, and we can just say that this limit right here, according to our definition of the integral down here, is just going to be equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. And now what we've changed here, you notice that x, now it's a continuous x, whereas here it was incremented x sub I. So now we've applied our definition of the integral, and we can actually translate this infinite sum into an integral that we can solve. So in order to solve this, we need to find f prime of x. We can just take our f of x from up here, and we're going to go ahead and bring it down, and then take the derivative of it, square that, and then take the square root of 1 plus that. Now it turns out these are typically more difficult to solve, because when you have that square root and you got the 1 plus that quantity in here, there's actually very few integrals or very few functions that we can actually solve this analytically for. Fortunately, our function here, we can solve it analytically. However, we're not going to do that for now. We can just plug this into DESMOS, and you can find that is actually 10.875. And let me just show you that. If let me zoom down here. So if we take the integral from 1 to 4 of square root of 1 plus f prime of x squared dx, we're getting 10.875. So DESMOS will do this immediately for us, which is convenient. And we see our value is 10.875, which gives us our exact arc length of 10.875, which apparently our n equals 100 estimate was good enough to 3 decimal places where it was actually sufficient. But now we've confirmed that we can get our exact arc length using calculus. So if you want to see how we actually solve this integral, I'm going to link this video to another one that goes through step by step how we could actually solve this out. It turns out it's not super easy, just because that square root kind of makes things difficult, but it's not too bad either. It doesn't take too long. So go ahead and link to the next one if you'd like to see this performed analytically.